Hi, today I'll be solving problem 10.5 in UGURAL. So we have a beam that has a distributed load across it and a point load at the end, at one of its ends, and it's rigidly supported. So we have to find the deflection at A and the slope at A using Castellino's theorem. So the first step will be to find the moment. So we're going to cut it. We can get this section. So we have our distributed load, we have our point load, P, and this distance is x. So setting the moment at the cut here equal to 0, we can get minus px plus m of x minus qx times x over 2, which is equal to 0. So minus px was the point load times the distance, and q was q times x to get the load, times it by half distance because that's where it has to travel. Solving for m of x, we get px plus qx squared over 2. And we know this is from 0 to L. So now we're going to have to use Castellino's theorem to find the deflection, which is the u over delta p equals to the integral from 0 to L of m over ei. Differentiate m with respect to p dx. So we know this. This we can easily get by differentiating m of x with respect to p, and we can get delta m p is equal to x. Okay, so now we can just plug in our numbers into it from 0 to L of m px plus q x squared over 2 times x dx. And we have ei, so we can either put it outside or we keep it inside. So t over ei. So now once we integrate, we're going to get 1 over ei px cubed over 3 plus qx4 over 8 0 to L. Apply. So now once we apply those, we're going to get pl cubed over 3ei plus qx4 over 8ei. Sorry, L4 over 8ei. And since our answer was positive, it means that the point load direction was correct. So that's the first part, to find the deflection at A. Now we're going to have to find the rotation at A, which is simply the same method, but we have to apply a virtual moment of C at A. So we're going to apply a virtual moment right here and call it C. So we're going to do the same thing. We're going to have another cut. We're going to have distributed load Q. We're going to have our point load P. And we're going to have C. This is our cut. Same thing, m of x. And then we're going to have the same thing. Basically, we're going to have the moment at the cut will equal to minus px minus m of x minus qx times x over 2. But we're going to add in c plus c. Set it equal to 0, and we can solve this. Get our m of x equal to px plus qx squared over 2 minus c, and it's again from x is from 0 to L. So now we're going to use Castellano's theorem, but for the slope, which is going to be 1 over EI from 0 to L of m, and then derivative of m with respect to c, which is our moment that we applied here, dx. So when we differentiate, we're going to get minus 1. So you can plug these values inside here. 1 over EI from 0 to L of px plus qx squared over 2 minus c times it by negative 1 dx. So once we integrate, we're going to get equal to 1 over EI minus px squared over 2 minus qx cubed over 6 plus cx from 0 to L. We're going to get our theta A is equal to minus PL squared over 2EI minus QL cubed over 6EI plus CL over EI. Since C was basically a virtual moment that we applied, we can now remove it. So we're going to set C equal to 0. So since it's a fictitious couple, set C equal to 0. And we're going to have this canceled out. And we're going to get our slope to be minus PL squared over 2EI minus QL cubed over 6EI. Alright, thank you very much.